Hey, welcome back to Fat Mama Physics. In these videos, we will be talking about Hooke's law. I will be mostly going over examples. I do expect you to have some understanding of what Hooke's law is. I will go over briefly the key things that I would like you to know before tackling these examples. So let's get started. Hooke's law states that a force needed to compress or stretch a spring is directly proportional to the distance pulled or pushed away from the spring's equilibrium position. So what does that all mean? So what I'm going to do is I am going to take a simulation to help us understand this. Here I got a spring, and here I got a little hand that's going to pull on a spring, which will apply a force. I'm going to turn on the equilibrium position, so that's that green dotted line. That's what that means. When the spring is not stretched or pulled, it's the tail end here is called the equilibrium position. Now, if I'm going to turn a few things on, such as the applied force, spring force, and displacement. So notice if I'm going to pull on this spring, I'm going to stretch it. Notice that my applied force, which is red, is increasing as I pull it, but then the more I pull on this spring, the more it wants to go back to its original position. And that's the restorative force that is inside the spring itself. It's shown in blue, called the spring force, or in other words, the restorative force. The interesting thing about the restorative force is that it opposes the direction of the displacement. So notice I am displacing my spring towards the right, while the spring force is trying to restore the spring back to the left, so back to its original position. Now if I compress the spring, notice my applied force is towards the left, displacement is towards the left, but spring force wants to push it back to the right side, to its original position. Okay, so that's the idea of Hooke's law. Notice we saw the restorative force, and because the spring's force is in the opposite direction of the displacement, you see this negative sign in this equation. So this equation is this force, restorative force, is directly proportional to how much I displace the spring from the equilibrium position. So x here is the displacement. What is the k though? The k is something called the spring constant. The spring constant tells you how stiff a spring is. The stiffer the spring, the harder it is to push or pull on it. So if I could here increase the spring constant of the spring, notice it gets a lot thicker and it takes a lot more force to get it to move, and this scale here is too small for that, so I can't get it to extend or stretch all the way. Larger spring constant, you need more force to displace the spring from its equilibrium position. Alrighty, now the next thing I would like you to know is when we graph the data. So for example, here I have a graph with the x-axis is how much I extend the spring. So that's the displacement from the equilibrium position, and the y-axis is the force that I'm applying, which is the applied force. And since it's equal and opposite to the restorative force, either one, I guess, works in terms of the magnitude. And here I can plot a graph in which the slope is the spring constant. And that's the other thing I want you to know. Since slope is rise over run, we have the rises as the force divided by the extension divided by the displacement x. And that's exactly, if I take this equation, I divide both sides by x, I get the spring constant, which is the other reason why the spring constant has units of newtons per meter, which you can catch that as you read the questions that come right now. So let's do the first problem together. I'll do example 1, you do example 2. Example 1, a 6.5 kilogram rock is stretched 4.5 centimeters horizontally on a slingshot If the sling acts like a spring, find. Okay, and then here's a brief picture just so you can visualize what's happening here. I have a sling, and then I have the rock being held back. So it's extending the sling here, and of course, if I let go, it's going to propel the rock forward like a slingshot. And we're going to treat it like a spring. But first, the question A says, we need to find the spring constant from the graph produced by stretching this sling. And we just talked about that. If it's a force displacement graph, then all we need to do is find the slope of the graph to get our spring constant. So let's do that now. Okay, so to get the slope of this graph, I do want to take points as far as I can. And these 2 points seem very viable. I'm going to take the endpoints, which is at the origin and here. That's very easy because all I need to do is I have a rise of 4 newtons and I have a run of 0.4 meters. Okay, if I divide the two, I get 10 newtons per meter. Seems like this graph is 1 sig fig, so we're going to take that 1 sig fig. 10 newton per meter is good, okay? The next up, we have question B. What is the rock's initial acceleration when released? Okay, so let's slow down there. So let's record a few things before we move on. First of all, we have a mass here, which is in kilograms. That's fine. We have a stretching of 4.5. Ooh, it's in centimeters, so we have to be careful about that. Usually when we deal with physics equations, most, if not all of our symbols, most of our unknowns need to be in meters when we put it in our equation. 4.5 centimeters divided by 100 centimeters per meter gives us 0.045 meters. Why we move the decimal place twice? 1, 2. I get 1, 0, decimal, and then 0 over there. That is our displacement. Okay, so now if I want to draw this picture here just to show you, so this rock here is stretched this much, and because it is stretched toward behind the slingshot, the sling is going to apply a equal and opposite restorative force back towards its original position, just like that. That is the spring force acting on the rock. Now, at this point, before this rock is released, there is technically an applied force which then causes the rock to not move. But the moment the rock is released, it will fly off. So at that point, the only force acting on the rock will be the spring force. So if I have to write an F net equation, I have F net as being the spring force, and then that equal to the mass times acceleration of the rock. And that's it. You might be thinking, what about gravity? Sure, there is gravity, but notice we are only talking about the horizontal. We're only talking about the horizontal forces acting on the rock right now. And you're right, to be more precise, this question should have said the rock's initial horizontal acceleration. So then we can just put in the x's here just to signify that. We also know that the spring force from what we saw earlier is equal to the spring constant times the displacement. I did not put a negative sign in here because I have already determined the direction that going backwards, when the direction the rock would be flung is in the positive direction, which is in line with the direction of acceleration of the rock. So I'm not going to put that negative sign there. I don't need it. I've determined my directions in my FNet. So let's substitute Fs in here. I get Kx equal to ma. And then to solve for the initial acceleration, I'm going to divide both sides by the mass. Okay, I'm going to substitute in my values. Don't forget this x just means horizontal there. I have K is 10 Newton per meter. I have X as 0.0045 meters and M as 6.5 kilograms. That's a big rock. I should have made it grams instead. Oh well. So let's put that in our calculator. So we get 0.069 ... meters per second squared, rounding up to 0.069. But the graph only shows us the 1 sig fig there, so I'm just going to write down again the proper number sig fig, 0.07 meters per second squared. So here's that. Okay. Sorry, there's an FG, that's not FA. Okay. Okay, and now we have your example. Example 2. Assuming you have a bow that behaves like a spring, you draw a 52-gram, that should say arrow. You draw a 52-gram arrow horizontally back 51 centimeters. Find the spring constant of the bow from the graph below. Oh, very similar. And then here again, find the initial acceleration, find the initial horizontal acceleration of the arrow upon release. Okay, so I'm going to give you a chance to do this question yourself. Here I'm going to zoom in so you can see the graph. Good time to pause and see you back. Okay, I will play my solutions on fast play. First, we need to grab the slope on this graph for the spring constant, picking the two furthest points. We get the rise as 20 newtons and the run at 0.1 meters. Dividing gives us 200 newton per meter. For the second question, we've got to draw a free body diagram, which I just took the time to draw a link there. And I just couldn't stop doing it. Alright, so the don't forget the arrow. The center of gravity is going to be closer to the tip of the arrow, which I did it roughly there. There is no really applied force after the arrow is released, just the spring force, in which it's the only net force acting on the arrow, and the spring force is kx, which we substitute that in, and solving for the acceleration, giving us kx over m. Don't forget the x, we need to convert the 51 centimeters to meters, and the 52 grams to kilograms by dividing by 1,000, and putting that all in our calculator, we get 1961, which then rounds to 2,000 meters per second square acceleration. Okay, and here's the solution to this problem. Very similar to the last one, except just be careful of converting your units. For example, your displacement, making sure it's in meters, and the mass, making sure to convert it from grams to kilograms. Sorry, I took some time to draw a link from Zelda games. Anyways, the arrow, notice I put the center of mass a little bit closer to the middle of the arrow. It's technically closer to the tip. Anyways, to show it's not at the base, not where the center of mass of the arrow is. Okay, here is the answer, around 2,000 meters per second square for 1 sig fig, because of this graph. So hopefully this wasn't too bad for you. There's still one more video coming for Hooke's law, another question. So hopefully you've learned something from this video you can apply in your questions. Thank you for watching this video, and Fat Mama Physics signing out.